The northern lights dance across the Arctic sky in ribbons of emerald and violet. But what if that breathtaking beauty is actually a cosmic warning sign? What if the shimmering aurora is a symptom of a deadly planetary condition, one that makes complex life like ours almost impossible to find in the universe? Today we are exploring a chilling idea called the Aurora Effect. This hypothesis suggests that the very forces that paint these brilliant lights in the sky, powerful solar storms and cosmic radiation, could be sterilizing planets and preventing the evolution of anything more advanced than microbes. By the end, you will understand why the search for alien civilizations might be far more difficult and far lonelier than we ever dreamed. We will uncover why a stable, gentle star like our Sun could be a rare cosmic treasure, and how a planet's magnetic field is not just a scientific curiosity, but a literal shield for all complex life. Are we playing a cosmic game of hide and seek where the rules are brutally unfair? What does it mean if the most common stars in the galaxy are also the most dangerous? The journey starts now. Do you believe we are truly alone in the universe? The silence of the cosmos is perhaps its loudest mystery. With hundreds of billions of stars in our galaxy alone, many hosting their own families of planets, the universe should be teeming with life. The math suggests a cosmic chorus of civilizations, their radio signals and megastructures lighting up the darkness. Yet when we listen, we hear only static. When we look, we see only empty space. This is the Fermi paradox, the profound and unsettling gap between expectation and reality. Where is everybody? One compelling answer to this question is the idea of a great filter. Imagine evolution from stardust to starfaring civilization as a long, treacherous obstacle course. The great filter is that one nearly impossible hurdle somewhere along the track, a stage so difficult that almost every competitor fails. It could lie in our past. Perhaps the jump from simple chemistry to the first living cell was a miraculous fluke. Or more ominously, it could still lie ahead of us, a future catastrophe waiting to wipe out advanced societies. The Aurora Effect proposes a specific, terrifying candidate for this filter. It suggests the hurdle isn't about intelligence or technology, but about basic planetary survival. Before a world can even dream of building radio telescopes, it must first survive its own star's tantrums. The filter, in this view, is the constant, brutal bombardment of radiation that strips away atmospheres and fries the surface. It is a bottleneck that crushes complex, multicellular life in its cradle, leaving behind a galaxy that may be rich in microbes but forever silent of voices. So the question shifts. We are not just asking why we do not see advanced aliens. We are asking how our own planet, against staggering odds, managed to slip through this cosmic gauntlet. Our own sun can seem so gentle and reliable, a steady beacon in the sky. But to understand the Aurora Effect, we must first confront a cosmic truth. Most stars are not like our sun at all. The most common type of star in the Milky Way, by a staggering margin, is the M-dwarf or red dwarf. These stars are smaller, cooler, and far more temperamental than our own. They are prone to frequent, violent outbursts, solar flares of immense power and coronal mass ejections that hurl vast clouds of charged particles into space. Now imagine a rocky, Earth-sized planet nestled in the so-called habitable zone of one of these red dwarfs. This zone is the distance where liquid water could exist. But here, the planet would be so close to its dim star that it becomes tidally locked, with one side in perpetual daylight and the other in eternal night. More critically, it would be sitting right in the line of fire. When a colossal flare erupts from that star, it is not a distant light show, it is a direct hit. The planet's atmosphere is bombarded with X-rays and ultraviolet radiation hundreds of times more intense than anything Earth receives. These energetic particles smash into the atmospheric molecules, stripping them away atom by atom, slowly bleeding the world's air into the void of space. This relentless erosion is the first act of the Aurora effect, but the violence does not stop there. Those charged particles, if the planet has a magnetic field, are funneled toward the poles. They collide with the remaining atmosphere and the sky ignites. The entire planet might be engulfed in a global, permanent aurora, a beautiful, terrifying symptom of its atmosphere being actively destroyed. On Earth, our auroras are a gentle side effect, a proof that our magnetic shield is doing its job, deflecting the solar wind and protecting our precious air. On a world orbiting a furious red dwarf, that same shimmering light could be a death knell. It is the visible sign of a biosphere under siege, a constant, luminous reminder that the star it depends on for warmth is also trying to kill it. This is the brutal heart of the Aurora effect hypothesis. It suggests that for the most common planets around the most common stars, the conditions needed for complex life, a stable, thick atmosphere and a radiation-shielded surface, are being systematically erased before life ever gets a chance to grow beyond the simplest forms. The beautiful lights in the sky are not a promise but a prognosis. These red dwarfs are not just common, they are the overwhelming majority. For every star like our Sun in the Milky Way, there are at least 3, perhaps 4, of these smaller, cooler M-dwarf stars. That means over 70% of all the stars in our galaxy fall into this category. Their sheer numbers make them the default setting for planetary systems. When astronomers scan the cosmos for other Earths, it is around these dim, red suns that they find the most promising candidates, worlds orbiting within the narrow band where liquid water could exist. The math seems encouraging. With so many stars and so many planets in their habitable zones, the galaxy should be a verdant place. But this is where the Aurora effect turns optimism into a profound caution. A red dwarf's habitable zone is a trap. Because these stars are so faint and cool, their zone of potential life is incredibly close in. A planet would have to orbit its star at a distance far smaller than Mercury's orbit around our Sun. This proximity creates 2 devastating problems. First, the planet becomes tidally locked. Just as our moon always shows the same face to Earth, a world this close to its star would have one hemisphere in permanent, scorching daylight and the other in endless, freezing night. The thin twilight band between them might be the only place with moderate temperatures, a precarious strip of real estate on a world of extremes. Second, and far more dangerous, this close orbit puts the planet directly in the line of fire. Young red dwarfs are notoriously violent, unleashing superflares with terrifying frequency. These are not like the solar flares we occasionally experience. A single eruption from a young red dwarf can be hundreds of times more powerful than anything in our Sun's recorded history. It would bathe the entire planet in a torrent of X-rays and ultraviolet radiation. For any life trying to gain a foothold, perhaps in a shallow sea or a damp patch of soil, these events would be apocalyptic. Imagine a world where, every few days or weeks, the sky explodes with an invisible fury that sterilizes the surface, shreds complex molecules, and drives any surviving life deep underground or into the absolute depths of an ocean. It is a cycle of creation and destruction where the star giveth warmth and then violently taketh away. This is the brutal reality for most planets in the galaxy's most common neighborhoods. The stage for life may be set, but the star itself is an arsonist, repeatedly burning down the theater before the play can even begin. Our own world is not immune to this cosmic violence. We have felt its sting, and the scars are written in our history. In September 1859, a colossal solar storm, now known as the Carrington Event, struck Earth. Telegraph systems, the high technology of the age, went haywire. Operators received shocks from their equipment, papers ignited from sparks, and the northern lights were seen as far south as the Caribbean. It was a spectacular and terrifying demonstration of our star's power. Today, a storm of that magnitude would be catastrophic. It would induce massive electrical currents in our power grids, potentially frying transformers and causing continent-wide blackouts that could take months or even years to repair. Satellites would be disabled, GPS and communications networks would fail, and we would be thrust back into a pre-electronic age almost overnight. This is not science fiction. Scientists warn it is a matter of when, not if, we face another Carrington-level event. Our modern civilization, for all its complexity, is balanced on a knife's edge, vulnerable to the tantrums of our own relatively quiet sun. Now project that vulnerability back in time to Earth's infancy. For its first billion years, our sun was not the stable beacon we know today. It was a T-Tauri star, a young, wildly variable sun prone to violent flares and eruptions far more frequent and powerful than anything we see now. The solar wind was a relentless hurricane. Our planet was bombarded by radiation and charged particles at a level that would be unsurvivable for any complex surface life today. So how did life not only begin but persist? The answer lies in the deep, dark ocean. The early Earth's vast global sea acted as a perfect shield, absorbing the deadly radiation and providing a stable, protected cradle. The first simple, single-celled organisms could thrive in those sunless depths, around hydrothermal vents or in the chemical-rich waters, completely insulated from the fury raging in the sky above. But here is the critical point of the Aurora Effect. For life to evolve beyond those simple beginnings, it had to leave that sanctuary. It had to venture into shallow waters, then onto land, to access new energy sources like sunlight. Each step upward was a step into a more dangerous, irradiated world. If the young sun's superflares were too frequent, too intense, they would have acted as a constant reset button. Every time a nascent ecosystem of more complex cells began to form in the sunlit shallows, a colossal solar storm could have scoured it clean, sterilizing the surface and pushing evolution back to the microbial safety of the deep. Our planet's journey from microbes to mammals required an incredibly long period of relative calm, a truce with our star. We had to wait for the sun to settle into its stable middle age, and we needed our planet's magnetic field to strengthen and stand guard. The Aurora Effect suggests that for many worlds that truce never comes. The star never calms down, or the planet never develops a strong enough magnetic shield. The result is a permanent lockdown where life is forever trapped in its simplest forms, hiding in the deep, while beautiful, deadly auroras blaze eternally in the toxic sky above. Earth's secret weapon is not its oceans or its atmosphere, but something invisible and immense. Our planet generates its own global force field. This is the magnetosphere, a vast, teardrop-shaped bubble of magnetic energy that extends tens of thousands of miles into space. It is our first and most vital line of defense. When the solar wind, that relentless stream of charged particles from the sun, comes screaming toward us, it does not hit our atmosphere directly. Instead, it encounters this magnetic shield. The particles are deflected, sliding around the edges of the bubble like river water flowing around a smooth stone. What we see as the gentle, dancing auroras at the poles are merely the few stragglers that get funneled down the magnetic field lines, a tiny leak in an otherwise impeccable defense. Without this shield, our atmosphere would have been stripped away billions of years ago, leaving a barren, irradiated rock. So what creates this life-preserving barrier? The answer lies in a cosmic engine deep within our planet. At Earth's core, a sphere of molten iron and nickel, heated by the radioactive decay of ancient elements, is in constant churning motion. This liquid metal conducts electricity, and as the planet rotates, it generates powerful electric currents. These currents, in turn, produce our global magnetic field. Scientists call this a dynamo. It requires a perfect recipe, a large, molten metallic core, rapid planetary rotation to stir that core, and intense internal heat to keep the convection going. Earth has all three. It is a geologically active world with a hot, liquid heart that spins once every 24 hours, constantly regenerating its protective magnetic bubble. This is the gold standard for planetary shielding, but how common is this recipe across the galaxy? For a rocky exoplanet orbiting a red dwarf, the odds are stacked against it. Remember, these worlds are often tidally locked. One side forever faces its star, the other faces eternal space. This dramatically slows their rotation relative to their star. A day might last as long as a year. That slow or even non-existent spin could be a death sentence for a magnetic dynamo. Without rapid rotation to churn the molten core, the internal engine could stall. The magnetic field weakens or fails to form at all. Even if a planet starts with a strong field, the constant, brutal battering from stellar flares could eventually erode its atmosphere faster than it can be replenished by volcanic activity. The planet is left naked. Its surface is exposed to the full, unfiltered fury of its star's radiation. Any complex organic molecules forming in ponds or seas would be shattered. The world might remain in a permanent state of sterile beauty, its skies lit by planet-wide auroras that signal not a thriving biosphere but a dying one. The Aurora Effect suggests that a strong, stable magnetic field is not a common planetary feature. It is a rare and precious alignment of geology, heat, and motion. For every Earth that spins its protective shield into existence, there may be countless other worlds, silent and exposed, where the stellar winds blow unchecked. But a magnetic shield is only half of the story. Even with a strong magnetosphere deflecting the solar wind, a planet needs a second, equally vital layer of protection. This is its atmosphere, a fragile blanket of gas that we rarely think about, yet it is the very thing that makes our world a living world. An atmosphere does far more than just give us air to breathe. It acts as a massive, planet-wide radiation shield. When high-energy ultraviolet and X-ray radiation from the sun streaks toward the surface, it does not get far. Molecules in our upper atmosphere, like ozone, absorb this dangerous energy, breaking it down into harmless heat long before it can reach the ground. Without this atmospheric filter, the surface would be bathed in sterilizing radiation, making the evolution of complex life on land utterly impossible. The atmosphere also creates the pressure needed for liquid water to exist. Without sufficient air pressure, water would instantly boil away into vapor, no matter the temperature. So this thin, invisible veil is not just a convenience, it is the container for the entire biosphere, the barrier between a thriving planet and a dead rock. But this blanket is terrifyingly fragile. It is under constant assault, and the primary weapon is the stellar wind itself. When a star unleashes a coronal mass ejection, it sends a billion-ton cloud of charged particles screaming into space at millions of miles per hour. If a planet's magnetic field is weak or misaligned, this torrent does not get deflected. It slams directly into the atmosphere. The process is called sputtering. Think of it like a cosmic sandblaster. High-energy particles smash into the molecules at the top of the atmosphere, knocking them loose with such force that they achieve escape velocity. They are literally knocked into space, lost forever. Over millions of years, this relentless erosion can bleed a world dry, stripping away its oceans, its air, and its future. We do not have to look far to see this tragedy in action. Our neighbor Mars is the perfect, heartbreaking case study. Billions of years ago, Mars was a different world. Evidence from rovers and orbiters shows it had vast oceans, flowing rivers, and a thick, protective atmosphere. It was a wet, warm world that could have been a cradle for life. But then, its planetary dynamo failed. For reasons we do not fully understand, its molten core cooled and solidified. Its global magnetic field collapsed. Left naked, Mars was exposed to the full fury of the young sun's solar wind. Without a shield, the atmosphere was systematically sputtered away into the void. The air pressure plummeted, The surface water evaporated and was lost to space or frozen underground. Within a relatively short cosmic timescale, Mars was transformed from a potential twin of Earth into the cold, desiccated desert we see today. Its rusty red color is not just dust, it is the rust of a world that bled out, the oxidized iron testament to a planet that lost its protective blankets and died. The Aurora Effect suggests that Mars is not a unique tragedy, but a common fate. For every planet that manages to hold onto its atmosphere like Earth, there may be 100 Mars-like worlds, their stories of potential life erased by the stellar winds, leaving behind only silent, beautiful wastelands under skies that once shimmered with the light of their own destruction. So the classic picture of a planet's potential is fatally incomplete. For decades, the search for alien life has focused on the Goldilocks zone, that narrow orbital band where a planet is not too hot and not too cold, where liquid water could theoretically pool on the surface. It is an elegant, simple idea. Find a rocky world orbiting within that sweet spot around its star, and you have found a candidate for life, but this concept is dangerously narrow. It treats a star as nothing more than a source of light and heat, a simple campfire in the cosmic dark. The reality is that stars are dynamic, violent, and messy. They are generators of ferocious space weather. This means the true habitable zone is not defined by temperature alone, but by safety. Astronomers now speak of a space weather habitable zone. This is a far more restrictive region where a planet must satisfy two brutal conditions. First, it must be the right distance to have liquid water. Second, and just as critically, it must be far enough from its star to avoid being fried by constant stellar flares and stripped bare by the stellar wind. A planet could be beautifully Earth-sized, with perfect oceans glistening under its sun. Yet if it orbits too close to a tempestuous star, those oceans will be boiled away and its atmosphere will be torn off, molecule by molecule, in a matter of millions of years. It is a world with all the right ingredients placed in an oven set to broil. This distinction shatters our optimism. The galaxy may be filled with planets in the traditional temperature-based Goldilocks zones, especially around plentiful red dwarfs. But the space where the habitable zone around those same stars could be vanishingly small or even non-existent. A star that flares violently every few days essentially has no safe harbor. Its entire system, no matter how many planets it hosts, is a shooting gallery. This dramatically shrinks the real estate for any life more complex than a hardy microbe. The cosmic neighborhood for civilizations is not just a quiet suburb with neatly spaced homes. It is a treacherous landscape where most properties are built on geological fault lines, in the path of constant hurricanes or downwind of an active volcano. The Aurora Effect tells us that finding a world with water is just the first, easiest step. The real challenge is finding a world that has managed to keep that water and the air above it for billions of years of relative peace. That is a much taller order, and it makes our pale blue dot seem less like a common model and more like a miraculously fortified castle in a universe of ruins. 3.5 billion years is an almost impossible span of time to truly grasp. It is the entire history of complex life on our planet, from the first faint whispers of single-celled organisms in the ancient seas to the technological civilization looking back at its own origins. That timeline is not a minor detail, it is the fundamental requirement. Life did not rush from microbes to mammals. It crept, it stalled, it experimented, and it survived countless near misses over an almost incomprehensible stretch of planetary history. This long, unbroken window of stability is likely non-negotiable. Evolution is not a sprint. It is an endless, slow-moving marathon run in the dark, where every runner needs a safe, well-lit path that does not suddenly collapse beneath their feet. The Aurora Effect introduces a brutal cosmic timer. It asks a simple, devastating question. What if most planets do not get 3.5 billion years of peace? What if their stars are ticking time bombs, resetting the evolutionary clock long before the finish line is ever in sight? Imagine a world orbiting a volatile red dwarf. Every few 100,000 years, or even more frequently, the star erupts in a superflare. The planet's atmosphere glows with a searing, global aurora as radiation scours the surface. Any complex molecules are shattered. Any ecosystems beginning to form in the sunlit shallows of an ocean are sterilized. The slate is wiped clean. Life, if it exists at all, is forced to retreat back to its simplest, most resilient forms, hiding in the deep ocean crust or buried in rock. It must start over again and again. On such a world, evolution is trapped in a loop. It is like trying to build a skyscraper while a hurricane blows through the construction site every few months. You can lay a foundation, but you will never get to the 10th floor. The progress is erased, the materials scattered, and the workers sent back to square one. This is the reset event, and if these catastrophic flares come too often, the planet never gets the consistent multi-billion-year truce that Earth enjoyed. There is never enough uninterrupted time for random mutations to accumulate, for cooperation between cells to begin, for the slow, miraculous journey from a single cell to a nervous system, to eyes, to a brain capable of wondering about the stars. The ladder of complexity is not just steep, it requires a stable floor to stand on for an almost eternal amount of time. The Aurora Effect suggests that for most worlds the floor is constantly shaking. The beautiful, deadly lights in their sky are not just a symptom of atmospheric loss. They are the flashing neon sign of a cosmic prison, a cycle of creation and destruction that forever traps life in its simplest, most silent form. This distinction is absolutely crucial, and it is where the full weight of the Aurora Effect comes crashing down. The universe may very well be swimming with life, but only of the tiniest, toughest, and most hidden variety. Consider the extremophiles right here on Earth. We find bacteria thriving in boiling geothermal vents at the bottom of the ocean, microbes locked in ancient Antarctic ice, and organisms flourishing in the radioactive environment of a nuclear reactor's cooling pool. These are the ultimate survivors, capable of enduring conditions that would be instantly fatal to any animal or plant. It is entirely plausible, even likely, that such hardy, single-celled life exists in the subsurface oceans of icy moons like Jupiter's Europa or Saturn's Enceladus, shielded from the deadly radiation of space by miles of solid ice. Life in its simplest form might be a cosmic inevitability, a tenacious spark that ignites wherever there is liquid water and a source of chemical energy. But there is an immense, almost infinite gap between a bacterium in a crack in the rock and a creature with a beating heart and a complex brain. The Aurora Effect does not argue that life is rare. It argues that complex life is the true cosmic miracle. That leap from a single cell to a multicellular organism is not a simple step. It is a revolutionary transformation that demands specific, stable, and long-lasting conditions. A microbe can hide, an animal cannot. Complex multicellular life, like all the plants and animals we see around us, has high energy demands. It needs sunlight for photosynthesis or abundant food sources that ultimately trace back to the sun's energy. This pulls life out of the safe, dark depths and up toward the surface into the light and directly into the line of fire from a hostile star. More than that, complex bodies require stability. Delicate processes like embryonic development, the functioning of intricate organs, and the maintenance of a nervous system cannot tolerate wild swings in temperature or sudden bursts of sterilizing radiation. A planet with a ravaged atmosphere and no magnetic shield offers no such stability. Its surface is a killing field, subject to lethal ultraviolet light, cosmic rays, and the periodic scouring of stellar flares. So the galaxy could be a vast, dark aquarium, filled with countless worlds where microbial life huddles in the mud, in the deep rock, or under icy shells. These are silent, simple biospheres. The Aurora Effect suggests that what is extraordinarily rare is the planetary nursery that can protect and nurture that life for billions of years, allowing it to grow bold, to experiment, to diversify, and to eventually crawl onto land and look up at the stars. Intelligence, consciousness, civilization, these are not just products of evolution. They are products of an almost unbelievable planetary peace treaty, one that our world has enjoyed, but one that may be violated on nearly every other world in the cosmos. The lights in the sky are not just beautiful, they are a boundary marking the difference between a universe that is merely alive and one that is truly awake. Our own solar system holds another, often overlooked guardian. Beyond the protective embrace of Earth's magnetic field, a second line of defense operates on a planetary scale. This is Jupiter, the gas giant, a titan whose silent work may have been essential for our existence. For decades, scientists have debated the Jupiter as a shield hypothesis. The idea is both elegant and terrifying. Jupiter's immense gravitational pull, over 2.5 times that of all the other planets combined, acts as a cosmic vacuum cleaner. It draws in or deflects countless comets and asteroids that might otherwise be on a collision course with the inner solar system. Think of it as a gravitational guardian at the gate, its sheer mass bending the paths of incoming debris, hurling it harmlessly into deep space or sometimes pulling it in to be consumed in its own thick atmosphere. We have seen this in action. In 1994, the world watched as fragments of comet Shoemaker-Levy 9, pulled apart by Jupiter's gravity, slammed into the gas giant in a series of spectacular explosions. Had that comet been on a different trajectory, it could have been headed for Earth. That event was a stark, real-time demonstration of Jupiter's protective role. A single impact from an object of that size on our planet would have been an extinction-level event, a global firestorm followed by a decades-long impact winter, wiping out most complex life. By taking these hits, Jupiter provides a quieter, more stable environment for the inner rocky worlds. It reduces the frequency of these civilization-ending catastrophes, granting Earth the long, uninterrupted stretches of geological time that complex evolution desperately needs. This suggests that a stable planetary system architecture is not a given. It is another piece of the rare Earth puzzle. A solar system needs its gas giants in the right places. A Jupiter too close to the Sun could destabilize the orbits of rocky planets, flinging them into the star or out into the void. A Jupiter that is absent or too small might leave the inner system exposed to a constant, deadly barrage from the Kuiper belt and the Oort cloud. Our system, with Jupiter in a distant, stable orbit, seems perfectly arranged for peace. This planetary teamwork is profound. Earth's magnetic shield defends against the silent, constant erosion from our star. Jupiter's gravity defends against the sudden, violent blows from the deep darkness. Together, they create a layered defense system, a safe harbor within a harbor. When we search for other Earths, we must now ask not just about the planet itself or its star, but about its entire celestial neighborhood. Does it have a giant guardian in the outer system, sweeping the lanes clear of existential threats? The Aurora Effect warns us of deadly skies, but perhaps equally rare is a clear and protected path through the cosmic debris field, a peace maintained by silent, distant giants whose own existence makes our fragile story possible. This invisible shield is the ultimate test for any world hoping to host a complex biosphere. Yet how can we possibly detect something as intangible as a magnetic field around a planet light years away? We cannot see it, we cannot touch it. We must look for its ghostly signature in the data, a whisper of its presence imprinted on the light of its star. This is the cutting edge of exoplanet science, a detective story written in radio waves and stellar flares. Astronomers have developed clever, indirect methods to hunt for these cosmic force fields. One promising technique involves watching for star-planet interactions. When a planet with a strong magnetosphere orbits very close to its star, its magnetic field can actually tangle with the star's own colossal magnetic field. This interaction can cause tiny but measurable brightening in the star's light at specific points in the planet's orbit, a flicker of increased activity as the fields connect and release energy. It is like hearing a faint, rhythmic hum from a machine whose inner workings we cannot see. Another method listens for a very specific sound. Charged particles accelerated by a planetary magnetic field should emit radio waves, a low-frequency crackle similar to the radio bursts we detect from Jupiter. If we could tune our telescopes to the right frequency from a distant star system, we might hear the distinct radio signature of an exoplanet magnetosphere, a beacon announcing its protective shield. But the challenges are immense. These signals are incredibly faint, drowned out by the radio noise of the star itself and the background static of the galaxy. Detecting the magnetic field of a gas giant close to its star is difficult enough. Confirming one around a small, rocky, Earth-sized world in the habitable zone is a monumental task, pushing our technology to its absolute limits. It requires exquisitely sensitive radio telescopes and often a bit of cosmic luck. We are, in essence, trying to spot a firefly's glow from across an ocean while standing next to a blazing lighthouse. This is why the Aurora Effect remains a compelling hypothesis rather than a proven law. We have the theory, the terrifying logic of atmospheric erosion and stellar fury. What we lack is the census. We do not yet know how many Earth-like exoplanets actually possess Earth-like magnetospheres. Every new telescope, every advance in detection, brings us closer to gathering the data we need. We are building the tools to take the galaxy's vital signs, to check for a pulse in the form of a magnetic field. The search is not just about finding new planets. It is about diagnosing them, determining which are robust and shielded, and which are exposed and dying. The answer will tell us if the beautiful, deadly auroras we envision are a common fate, or if fortresses like Earth are waiting silently in the dark. Just 4.2 light-years away, a world hangs in the balance. Proxima Centauri b is the closest known exoplanet to Earth, a rocky world roughly our own size, orbiting within the habitable zone of our nearest stellar neighbor. On paper, it is a dream discovery. In reality, it may be the perfect case study for the Aurora Effect, a living laboratory of cosmic hostility. Proxima Centauri is not a gentle sun like our own. It is a small, furious red dwarf, and it is a notorious flare star. Astronomers have watched it erupt with terrifying violence. In March 2016, the star unleashed a superflare so powerful that, for about 10 seconds, it became 10,000 times brighter in ultraviolet light. If you were standing on the surface of Proxima b during that event, the sky would have erupted in a flash hundreds of times brighter than our sun at noon. The planet was bathed in a wave of radiation that would deliver, in mere moments, the equivalent of thousands of years' worth of Earth's normal exposure. Imagine the ozone layer of an entire planet being chemically shredded in an instant. This is not a rare, once-in-a-lifetime event for this system. Proxima Centauri produces these powerful flares with alarming regularity several times a year. The planet is in a constant state of siege, its atmosphere hammered by X-rays and ultraviolet radiation that break apart the very molecules of air, turning them into atoms that can more easily escape into space. Given its extremely close orbit, Proxima b is almost certainly tidally locked. One hemisphere is a scorching, permanent day under the dull red glow of its star. The other is a frozen, eternal night. Only a thin, treacherous twilight band along the terminator line might offer moderate temperatures, but even there, the surface would be lethal. Without a robust magnetic field, something incredibly difficult to generate on a slowly rotating, locked world. The planet has little defense. Scientists running sophisticated climate models have reached a grim conclusion. Even if Proxima b started with a thick, Earth-like atmosphere and global oceans, the relentless barrage of stellar flares would have stripped it bare within a mere 100 million years. That is a geological blink of an eye. any water would have been lost to space, leaving behind a desiccated, irradiated rock. The beautiful, haunting possibility of a nearby Earth twin collapses under the harsh light of stellar reality. Proxima b stands as a stark poster child for the Aurora Effect. It ticks every box: a common star type, a planet in the classic habitable zone, and a fate likely dictated by relentless space weather. It is a world that, by the old, simple rules of astrobiology, should be a prime candidate for life, but under the new understanding, it is a monument to a cosmic bottleneck. Its skies, if any atmosphere remains at all, would shimmer with constant planet-wide auroras, a spectacular global funeral pyre for its potential biosphere. This is not science fiction, this is the data from our closest neighbor. If this is the reality next door, what does it suggest about the millions of similar worlds orbiting similar stars across the galaxy? The silence from Proxima b may be the most eloquent answer we have ever received. The story of Proxima b forces us to confront a humbling cosmic perspective. For decades, a compelling idea known as the rare Earth hypothesis has argued that planets like ours are not just lucky, but astronomically improbable. It is a checklist of galactic fortune, a list of conditions so specific and interconnected that finding another world that meets them all seems like searching for a single, perfect grain of sand on every beach across the planet. This list is long and daunting. It includes a stable, middle-aged star like our Sun, not too hot and not too cool. It requires a rocky planet of the right size, with plate tectonics to recycle nutrients and regulate climate through the carbon cycle. It needs a large moon to stabilize the planetary tilt, preventing wild swings in seasons that would make complex ecosystems impossible. It demands a safe location in the galaxy, far from the sterilizing radiation of the galactic core and away from dense star clusters where gravitational chaos reigns. And now, the Aurora Effect adds a critical, terrifying new line to that checklist. It argues that beyond the right star, you need a quiet star. Beyond the right orbit, you need a shielded orbit. Stable space weather is not a bonus feature. It is a foundational requirement, perhaps one of the most stringent and overlooked filters in the entire cosmic evolutionary process. Think of it this way: you could have a planet that passes every other test on the rare Earth list. It has perfect water, a giant moon, a perfect orbit around a G-type star like our Sun. But if that particular star has a hyperactive, violent youth that lasts too long, or if the planet's internal dynamo fails to spark, the game is over before it even begins. The atmosphere evaporates, the surface is sterilized, all that other perfection is rendered meaningless. The Aurora Effect narrows the window of possibility even further. It suggests that the habitable zone is not a place, but a state of being, a delicate balance between receiving enough warmth and avoiding too much fury. This transforms the rare Earth hypothesis from a compelling argument into a potentially devastating verdict. It is no longer just about having the right ingredients in the pantry. It is about having a kitchen that is not on fire. The beautiful, shimmering auroras we admire on Earth are proof our shield is working. But across the galaxy, that same shimmering light may be the most common glow in the darkness, a universal sign that for countless worlds, the cosmic conditions for a quiet, billion-year childhood simply never align. We are not just rare, we are the beneficiaries of a celestial peace treaty that may be one of the universe's best-kept secrets. Yet this cosmic loneliness is not the only possible story. The Aurora Effect presents a stark and compelling argument, but science thrives on debate, and other researchers offer crucial counterpoints that paint a less desolate picture. They remind us that planetary survival is a dynamic battle, not a predetermined sentence. For instance, a world with an initially much thicker atmosphere than Earth's could withstand the erosive power of stellar winds for far longer, buying precious time for life to gain a foothold and perhaps even for a magnetic dynamo to kick in. Volcanic activity, too, is a planetary life support system. constantly venting new gases from the mantle to replenish what is lost to space. A geologically active world might maintain its atmospheric pressure through a constant, slow leak and a constant, slow refill. Then there is the sheer stubbornness of life itself. We assume complex organisms need Earth-like conditions, but evolution is endlessly inventive. Could life on a high-radiation world adapt in ways we cannot yet conceive? Perhaps with biochemical shields, or by living in mineral layers just beneath the surface that filter out the deadly rays. There is also the profound potential of subsurface oceans, like those on Europa or Enceladus, sealed away under miles of ice. These are perfectly shielded environments, bathed in chemical energy from hydrothermal vents. While the Aurora Effect argues such places trap life at a microbial stage, some scientists wonder if that is truly a permanent limit. Given billions of years of isolation and evolutionary pressure, could a complex, even intelligent, ecosystem evolve in a totally dark, underwater world? It might never build radio telescopes, but it could represent a form of complexity utterly alien to our sunlit experience. These debates are not about dismissing the Aurora Effect, but about refining it. They highlight that we are still in the earliest chapters of understanding planetary habitability. Every new exoplanet discovered adds a new data point, a new surprise that challenges our assumptions. The universe has a habit of being more creative than our models, so while the hypothesis forces us to confront a terrifying galactic filter, it is not yet a final verdict. It is a crucial warning against naive optimism, a framework that asks the right, difficult questions. The search continues, now with a sharper eye for not just water and warmth, but for magnetic fields, atmospheric composition, and stellar temperaments. The great silence may yet be broken by a signal from a world that defied all the odds, a world that found another way to survive the storm. This search for other minds has a name, and it is built on a profound hope. The search for extraterrestrial intelligence, or SETI, has spent decades listening for a whisper in the cosmic static, a deliberate signal that says, "We are here." It operates on a beautiful, optimistic assumption that if life can become complex and intelligent elsewhere, it will also become communicative, building technologies like radio transmitters that we might detect across the light years. But the Aurora Effect casts a long, cold shadow over this entire endeavor. It proposes a universe where the great filter is not about intelligence, but about survival long enough to use it. If complex, multicellular life is the true miracle, then the pool of potential civilizations shrinks from a vast ocean to a few scattered drops. We would not be searching for a galaxy buzzing with conversation. We would be searching for a handful of survivors in an infinite graveyard of silent, microbial worlds. The tools of this search are divided into two categories, and the difference between them is now critical. Biosignatures are signs of any life, however simple. Think of the chemical composition of a planet's atmosphere. On Earth, the large amount of oxygen and the presence of methane, a gas that is quickly broken down by sunlight unless it is constantly replenished, together scream life. A future telescope might detect that same unbalanced chemistry on a distant exoplanet and announce the discovery of a living world. But that world could be a global bacterial mat, a slime-covered rock. Technosignatures, however, are the fingerprints of a technological civilization. These are the signals SETI has traditionally sought. Narrowband radio transmissions, laser pulses, the spectral signature of artificial pollutants in an atmosphere, or even the faint shadow of a vast megastructure orbiting a star. The Aurora Effect suggests a heartbreaking decoupling of these two searches. We may, in the coming decades, find a bounty of biosignatures. Our telescopes might catalog dozens, even hundreds of worlds with atmospheres chemically altered by simple life. But technosignatures could remain elusive, not because civilizations are hiding, but because they almost never exist in the first place. The galaxy could be a garden of microbes, forever pruned back by stellar fury before any flower of intelligence can bloom. This realization forces a radical shift in strategy. If technological civilizations are the rarest of cosmic events, then listening for their active broadcasts might be like hoping to hear a specific conversation in a city that has been abandoned for millennia. We need to broaden our search to look not just for a signal but for an echo. One approach is to search for signs of ancient, possibly extinct civilizations. This is archaeology on a galactic scale. Instead of listening for a hello, we would look for the ruins. Could our telescopes detect the long-cooled remains of a Dyson sphere, a vast shell of solar collectors built by a civilization that harnessed its star's total energy? Could we find evidence of planetary-scale engineering, like a climate control system that left a permanent chemical mark on a world's geology long after its builders were gone? We might even look for evidence of a civilization's self-destruction, like the isotopic signature of a global nuclear war preserved in the dust of a distant exoplanet's atmosphere. These are not signals of communication, they are tombstones. Another strategy is to look for the unintentional byproducts of a civilization's energy use, even if that civilization is not trying to talk. Every advanced society will generate waste heat, a thermal signature detectable in the infrared. On Earth, our cities are islands of heat visible from space. A truly advanced, galaxy-spanning civilization might produce a waste heat signature so large it alters the expected infrared output of its entire star system. We could also search for evidence of industrial pollution. Certain artificial chemicals like chlorofluorocarbons are incredibly stable and would persist in an atmosphere for tens of thousands of years. Detecting them on a distant world would not mean we found someone to talk to. It would mean we found the empty, still smoking factory, a relic of a society that flared brightly and then went dark. This shifts SETI from a hopeful conversation to a SAMA cosmic forensics investigation. We are no longer just listening for a voice. We are sifting through the ashes of cosmic history, looking for the faint, cold traces of a fire that burned once and only once against an endless night. Our own planet does not hold a monopoly on these shimmering lights. Across our solar system, auroras paint alien skies, revealing the hidden forces at work on other worlds. Take Jupiter, the king of the planets. Its auroras are not gentle ribbons. They are colossal, permanent rings of fire, each larger than our entire planet, blazing with ultraviolet and X-ray light invisible to our eyes. The energy source is staggering. Jupiter's magnetic field is the most powerful in the solar system, a magnetosphere so vast it would appear larger than the full moon in our sky if we could see it. But the fuel for its incredible light show comes from an unexpected place, its volcanic moon, Io. Io spews tons of sulfur and oxygen into space every second. These particles become ionized, caught in Jupiter's magnetic grip, and accelerated down the field lines toward the poles at nearly the speed of light. When they slam into the atmosphere, they unleash a torrent of energy, creating auroras hundreds of times more powerful than Earth's. Here, the aurora is a spectacle of pure, raw power, a testament to a magnetic field so strong it turns a moon's volcanic fury into a celestial beacon. Now consider the opposite extreme. Look to our neighbor, Mars. The red planet also has auroras, but they are ghostly, diffuse, and strange. Unlike Earth's organized rings or Jupiter's blazing crowns, Martian auroras are patchy and sporadic, appearing in random locations across the night sky. The reason is written in the planet's ancient rocks. Mars lacks a global magnetic field. Instead, remnants of its past dynamo are frozen into the crust, creating isolated pockets of magnetism like scattered, invisible umbrellas. When the solar wind hits Mars, it bypasses these weak, localized shields and strips the atmosphere away across most of the planet. But in those few protected spots, charged particles can funnel down to the surface, igniting faint, dancing lights. These are not signs of a healthy shield. They are the flickering candles of a world that lost its main power source, glimpses of light in a global atmospheric hemorrhage. These two examples, Jupiter and Mars, bookend the story told by the Aurora Effect. The phenomenon itself, charged particles exciting an atmosphere, is universal. But the context is everything. On a world like Jupiter, with a magnetic field of godlike strength, the aurora is a byproduct of immense control, a contained and managed release of energy. On a world like Mars, with a failed or absent dynamo, the aurora is a symptom of systemic failure, a sign of the atmosphere bleeding away under an unblocked stellar wind. One is the light of a fortress in full command of its defenses. The other is the light of a ruin, its walls breached, its interior exposed to the elements. When we look out at the galaxy and imagine other Earths, we must therefore listen to what their auroras would tell us. Is that distant shimmer the proud banner of a shielded, thriving world, or the final, beautiful gasp of a biosphere in its death throes? The difference is the difference between a cosmos that is merely alive and one that is truly, enduringly awake. Earth's magnetic fortress is not a permanent monument. It is a living, breathing, and ultimately temporary phenomenon. Deep within our planet, the churning dynamo that generates our shield is powered by a finite source of heat, the slow radioactive decay of elements, and the residual warmth from our planet's violent formation. Over billions of years, this engine will cool. The molten outer core will gradually solidify, the convection currents will slow, and the magnetic field will begin to fade. This is not speculation. It is the inevitable fate of every rocky world with an iron heart. The geological record tells a dramatic story of this dynamo's past behavior. Our magnetic field is constantly shifting, its strength waxing and waning. Most strikingly, it occasionally flips entirely, with the north and south magnetic poles swapping places. During these chaotic transitions, which can take thousands of years, the field weakens dramatically, becoming a patchwork of multiple poles, a fractured and feeble shield. We are already living in a period of measurable weakening. The South Atlantic Anomaly, a vast region over the Atlantic Ocean where the field is significantly thinner, is a present-day reminder of this vulnerability. Satellites passing through this zone experience higher radiation levels and increased risk of electronic glitches. It is a quiet preview of a far more precarious future. Now project that forward. Imagine Earth a billion years from now with a magnetic field at only a fraction of its current strength. The solar wind, once deflected with ease, now presses closer to the atmosphere. The beautiful, contained auroras at our poles begin to spread, becoming more frequent and intense at lower latitudes, not as a gentle light show, but as a symptom of atmospheric erosion. With each passing eon, the relentless sputtering process would accelerate. Our atmosphere, no longer held tightly by a robust magnetic grip, would start to bleed away into space, molecule by molecule. The air pressure would drop, the sky would thin. The protective ozone layer, battered by unfiltered ultraviolet radiation, would degrade. Complex life on the surface, adapted to a specific and stable environment over eons, would face an existential threat. The very conditions that allowed our ancestors to crawl from the sea and eventually look to the stars would be slowly, irrevocably undone. This ties the cosmic hypothesis directly back to our own home. The Aurora Effect is not just a story about alien worlds. It is a possible chapter in Earth's own distant future. Our planet's protective bubble, so crucial for our existence, is a lease, not a deed. It grants us a long, glorious tenure in the cosmic neighborhood, but the lease will eventually expire. On a geological timescale, even Earth is not immune to the forces that may have silenced countless other worlds. Our shield will one day fail, and when it does, the beautiful, deadly lights in the sky will signal not just a change in the weather, but the beginning of the end for the complex, vibrant biosphere we call home. This realization adds a profound layer of urgency to our search for other civilizations. We are not just looking for company in the cosmos. We are looking for evidence that others have navigated this long, treacherous timeline, that the window for intelligence and civilization can stay open long enough to be seen across the light years. Are we an early bloom in a cosmic spring, or are we watching the last sunset on a planet that has already outlived all its peers? The silence of a galaxy filled with only microbes is a haunting possibility, but intelligence, should it ever emerge, is a force of relentless ingenuity. If a species can survive the cosmic gauntlet long enough to build a civilization, could it then learn to defy the very forces that nearly wiped it out? Could an advanced intelligence engineer its own salvation, transforming a hostile world into a shielded haven? The answer moves us from astrobiology into the realm of planetary-scale engineering, a testament to what a conscious technological mind might achieve. The most direct solution to the Aurora effect is also the most audacious, building a planetary magnetic field. For a world whose internal dynamo has failed, like Mars, this is the ultimate terraforming prerequisite. Without a magnetic shield, any atmosphere we might create would simply be stripped away again by the solar wind, a futile exercise in cosmic landscaping. So how could it be done? One theoretical proposal involves placing a powerful, artificial magnetic dipole at a stable point between the planet and its star. This would not be a small device. It would likely be a massive superconducting ring, miles in diameter, generating a magnetic field strong enough to envelop the entire planet in a protective bubble, deflecting the stellar wind just as a natural magnetosphere does. The energy requirements would be staggering, perhaps on the scale of harnessing a significant fraction of the star's total output. Another idea leverages the planet itself. We could attempt to restart its core. This might involve using focused nuclear detonations deep within the mantle to generate heat and motion, or even dragging a large asteroid into a precise, grazing impact to transfer immense kinetic energy and stir the planetary interior. It is planetary surgery on a scale we can barely conceive, a project spanning centuries. The goal is not just to create an atmosphere, but to build the machine that keeps it safe. This is the difference between pitching a tent and constructing a fortified, climate-controlled dome over an entire world. Before such global engineering, a younger civilization might opt for more contained survival. Vast, interconnected habitats buried deep underground or encased in radiation-shielded domes could shelter a population from a lethal surface. They could tap geothermal energy, cultivate food in artificial biospheres, and create a sustainable existence entirely divorced from the hostile sky. Their world would not be the planet, but the architecture they build within it. This is a plausible path, but it carries a profound limitation. A species living in permanent bunkers, no matter how vast, is inherently constrained. Their growth, their resource base, their very connection to a natural world is severed. Expansion becomes a logistical nightmare of building more sealed habitats rather than stepping out into open air. It is a life of survival, not necessarily of flourishing. It raises a somber question. Could a civilization that never feels the wind on its face or sees an unaltered horizon ever develop the same drive to explore the cosmos? Their entire existence might be focused inward on maintaining the integrity of their shell, making them invisible to our searches for technosignatures. They would be the ultimate survivors, but not necessarily the starfarers we imagine. This brings us back to our own backyard and the dream of terraforming Mars. Current plans focus on the relatively easier steps, releasing greenhouse gases from the polar caps and soil to thicken the atmosphere and warm the planet, perhaps introducing engineered microbes to produce oxygen. But all these efforts hit the same fundamental wall outlined by the Aurora effect. Without a magnetic field, any atmosphere we painstakingly create on Mars will be ephemeral. The solar wind will chip away at it, undoing our work over millions of years. For humanity to truly claim Mars as a second home, we would not just need to give it air and water. We would need to give it a heart, a spinning, molten core that can generate a protective shield. That task is, with any technology we can foresee, Herculean. It suggests that true planetary engineering is not for a species taking its first steps into space. It is for a mature, patient civilization thinking in geological time, one that has mastered energy and matter to the point of becoming a steward of worlds. So the Aurora Effect presents two visions. One is a galaxy where the filter is absolute and complex life is forever trapped or erased. The other is a galaxy where the rarest of intelligences, having barely survived their violent stellar cradles, learn to become architects of their own destiny. They would not just find habitable planets, they would learn to build them. Their greatest technosignature might not be a radio signal, but the sudden, inexplicable appearance of a magnetosphere around a once dead world, a lighthouse of engineering shining across the light years. This leads us to a profound and somewhat dizzying philosophical twist. We are here on this shielded world, asking why we do not see others like us, but what if our very existence is the answer? This is known as the anthropic principle. In its simplest form, it states that the universe must be compatible with the existence of observers because we are here to observe it. We are not a random sample of cosmic reality. We are a product of its most exceptional conditions. Applied to the Aurora Effect, the logic is stark. We find ourselves on a planet with a stable magnetic field, a quiet sun, and a multi-billion-year peace treaty because if we were on any other kind of world, we would not exist to ponder the silence. Our presence is not evidence that such worlds are common. It is absolute proof that they are possible at least once. Imagine you are the sole survivor of a shipwreck washed ashore on a tiny, perfect island. You look out at the endless, empty ocean and ask, where are all the other survivors? The answer is tragically obvious. They did not make it. You are not on the island because islands are everywhere. You are on the only island that existed for you to reach. Your perspective from that safe beach is fundamentally biased. You might assume the sea is dotted with similar havens simply because you found one. But the vast, drowning expanse tells a different story. This is our cosmic situation. Our viewpoint from Earth is the ultimate survivor's bias. We look out from a fortress that passed every filter and assume the galaxy must be filled with similar strongholds. But the Aurora Effect suggests we are looking out from the one lighted window in a city of darkened ruins. Our science, our astronomy, even our questions are all filtered through this privileged and potentially very lonely vantage point. It means the universe we perceive is not a representative slice of reality. It is a carefully curated exhibit, one where all the conditions for our existence have already been met. The silence we hear is not a puzzle to be solved from a neutral position. It is the expected background noise of a cosmos where the conditions for asking the question are themselves the rarest of cosmic events. So when we point our telescopes and find only sterile rocks or volatile stars, we should not be surprised. We are not finding a universe hostile to life. We are finally seeing the universe as it truly is for almost everyone and almost everything else. We are the exception gazing out at the rule. The universe may seem distant, but its lessons echo right here at home. We have been exploring a cosmic threat, a stellar storm that could sterilize planets. Yet there is another storm brewing, one we created ourselves. The parallel is chilling. The Aurora Effect describes a world made vulnerable to the fury of its star, its protective shields failing under an external assault. Climate change describes a world made vulnerable by the actions of its inhabitants, its protective systems failing under an internal pressure. Both are stories of a delicate balance being pushed toward a breaking point. Both threaten the very stability that allows a complex, technological civilization to not just arise but to endure. Our planet's atmosphere, that thin, vital blanket, is the common battleground. In the cosmic scenario, a weak magnetic field lets the solar wind erode the atmosphere away into space. In our terrestrial reality, the relentless emission of greenhouse gases is thickening that same atmosphere, trapping excess heat and destabilizing the global climate systems that have nurtured us for millennia. The mechanisms are opposites. One strips away, the other smothers, but the potential outcome is similarly dire. A world rendered hostile to the complex life it once cradled. Think of Earth's climate as a patient in a carefully controlled hospital room. For billions of years, natural cycles have maintained a stable temperature, a balanced chemistry, a reliable rhythm of seasons. This stability provided the long, quiet corridor of time evolution needed. Now we are drastically altering the room's thermostat, its air composition, and its pressure all at once, and at a rate far faster than the patient's systems can adapt. This is not just an environmental issue, it is a crisis of planetary habitability. The ice caps melting, the oceans acidifying, the jet streams shifting. These are not isolated events. They are symptoms of a fundamental change in the operating conditions of our only biosphere. We are conducting a reckless, planet-wide experiment with the very systems that keep us alive. The Aurora Effect teaches us that such systems are not guaranteed. They can be lost. We see the evidence on Mars, a world that lost its magnetic shield and then its atmosphere, transforming from a wet, potentially life-friendly planet into a frozen desert. That is a cosmic cautionary tale written in rust. Our story does not have to end that way, but it underscores a profound truth. The conditions for a civilization like ours are not a permanent default setting. They are a temporary, precious, and fragile alignment. Recognizing our vulnerability to a stellar storm from light years away should sharpen our focus on the vulnerability we are manufacturing right beneath our feet. It frames Earth not just as our home, but as a lifeboat in a vast and mostly empty ocean. We are simultaneously the crew and the only passengers. Puncturing that lifeboat through neglect or short-sightedness would be a tragic irony of cosmic proportions. We would be succumbing to a filter of our own making, having miraculously survived the natural ones. The silence out there may be a testament to how rare and difficult this journey is. The question now is whether the greatest threat to our continued chapter is truly from the distant stars, or from the choices we make in the mirror of our own world. The next decade will transform speculation into data. A new generation of cosmic observatories, more powerful than any before, is being pointed at the stars with a single, profound question in mind. Are worlds like Earth the rule or the breathtaking exception? The James Webb Space Telescope is already revolutionizing this search. Its incredible sensitivity allows it to do something once thought impossible: analyze the chemical composition of atmospheres around distant Earth-sized exoplanets. Scientists are not just looking for water vapor or oxygen. They are hunting for specific, telltale signs of atmospheric erosion. Imagine Webb staring at a planet like Proxima b. If its atmosphere is being stripped away by stellar flares, the data might show a puff of hydrogen gas trailing behind the planet like a comet's tail, a clear fingerprint of atmospheric loss. Or it might detect a complete absence of certain molecules that should be there, suggesting they have already been blasted into space. Webb provides the crime scene photos, the forensic evidence of whether a world's air is intact or bleeding away. But to understand the crime, we must also study the weapon. Closer to home, a fleet of dedicated space weather observatories keeps a constant, vigilant watch on our own sun. Missions like the Parker Solar Probe are flying daringly close to our star, touching the very edge of its corona to understand the fundamental physics of the solar wind and coronal mass ejections. By learning exactly how our sun generates its fury, we can build better models to predict the behavior of distant, more volatile red dwarf stars. It is like studying a controlled fire to understand the dynamics of a wildfire. This ground truth from our own solar system is essential for interpreting the chaotic data we receive from light years away. The ultimate goal, however, is to find the shield itself. Detecting a magnetic field around a small, rocky exoplanet remains one of the greatest technical challenges in all of astronomy. the solution may come from a new kind of ear on the universe. Next-generation radio telescopes, like the sprawling square-kilometer array being built across 2 continents, will listen for the universe in unprecedented detail. Their design allows them to tune into the faint, low-frequency radio crackle that a planetary magnetosphere should emit. It is the sound of a force field at work. If they can pick up that specific signal from a world in a habitable zone, it would be a discovery of monumental importance. It would not just find a planet. It would diagnose it as protected, as fortified, as a potential sanctuary in the storm. Each of these tools offers a different piece of the puzzle. Webb tells us about the atmosphere's health. Solar probes teach us about the stellar threat, and radio telescopes might finally let us hear the hum of a distant planetary shield. Together, they form a detective's kit for cosmic habitability. Within the next 10 to 20 years, the data from these missions will begin to flood in. We will move from having a handful of intriguing but ambiguous exoplanets to having a statistical sample of hundreds with known atmospheric properties and perhaps confirmed magnetic fields. This hard data will either validate the terrifying logic of the Aurora Effect, showing us a galaxy littered with eroded worlds, or it will reveal a universe more resilient and ingenious than we dared hope, filled with fortresses we have yet to understand. The great silence is about to be broken not by a message, but by a million points of light, each one telling its own story of survival or surrender. The data will soon tell us which vision of the cosmos is true. We stand at a crossroads between 2 profound and profoundly different universes. In one, the Aurora Effect is a dominant galactic reality. Here, the universe is a quiet cathedral. Its halls are filled with countless worlds where life exists only as a whisper, a film of bacteria under ice, a community of extremophiles in a deep rock fissure, a silent, dark ocean beneath a frozen crust. These are biospheres of profound simplicity, enduring in their isolation but forever trapped. They represent a universe that is biologically alive yet intellectually silent. The Great Filter is real, and it is the violent adolescence of stars and the failure of planetary shields. In this cosmos, we are not just alone in our neighborhood. We might be alone in the entire gallery of existence that cares, thinks, or wonders. The shimmering auroras across the galaxy are funeral lights for a trillion unrealized dreams. Yet another universe is possible, one of stubborn, irrepressible creativity. In this version, life does not just endure, it adapts and overcomes in ways we cannot yet fathom. Perhaps on a world with constant flares, life evolves with natural biological shielding, or develops a society entirely within planet-spanning, subterranean networks. Maybe intelligence arises not in sun-drenched forests, but in the perpetual dark of a subsurface ocean, communicating through pressure waves or bioluminescent patterns we would never think to look for. This is an optimistic view where consciousness is not a fragile accident, but an inevitable flowering of complexity, emerging in forms utterly alien to our own experience. The silence we perceive is not absence, but a failure of translation. We are listening for a radio signal in a symphony played with instruments we do not recognize. Both possibilities carry a weight that extends beyond astronomy. If we are truly rare, then our existence is a statistical miracle of staggering proportions. Every breath of air, every sunset, every thought is the product of a chain of cosmic luck so long it defies comprehension. This perspective instills not arrogance, but a deep and humbling responsibility. It means this pale blue dot, with its magnetic shield and its stable sun, is not just our home. It is a sanctuary of near impossible value in a vast and mostly inhospitable universe. Protecting its delicate balance becomes a sacred duty, not just for ourselves, but as stewards of a flame that may be one of the very few in all the darkness. Conversely, if we are not alone and intelligence is common, then a different question arises. Where are they? The continued silence suggests that perhaps all advanced civilizations face a common, insurmountable challenge, not from their stars but from themselves. The filter may not be astrophysical but societal. It could be that the technological power to communicate across the stars is always coupled with the power for self-destruction, through war, environmental collapse, or some peril we have yet to encounter. In that case, the Great Silence is a warning, a library of histories where every civilization reached a certain point and then went quiet. We are listening for an answer, and the answer we are getting might be a cautionary tale. So we are left to ponder, armed with our telescopes and our theories, on the edge of a great revelation. Are we the lonely guardians of a rare and precious spark of consciousness, looking out at a galaxy of beautiful, barren rocks? Or are we simply young, surrounded by neighbors whose language we have not yet learned to hear? The coming flood of data will push us toward one answer or the other. But until then, we hold both truths in our minds. This duality itself is a gift. It forces us to cherish our world with the fervor of those who might be the universe's only witnesses, while still daring to hope that one day the silence will break and we will finally know we are not the only ones wandering in the night. The surface of this world is a monument to cosmic violence. Under the dull, crimson glow of its star, the landscape is a cracked and barren plain, painted in hues of rust and ash. There is no rustling of leaves, no call of birds, only the whisper of a thin, toxic wind scouring rock that has been sterilized by ultraviolet light 1,000 times over. The sky is not blue, but a perpetual, shimmering veil of sickly green and violet. This is not an occasional light show at the poles. It is a planet-wide aurora, a constant, beautiful hemorrhage as the last remnants of atmosphere are excited into glowing by the relentless stellar wind. The very air is being torn away, and the sky itself is the visible symptom of the planet's slow death. On the day side, permanently locked facing the star, the ground may be hot enough to melt lead in places. On the night side, an eternal, deep freeze preserves a silent desert of ice and dust. Only along the razor-thin terminator line, the border between eternal day and endless night, might temperatures approach anything we would recognize. But even there, the surface is lethal, bathed in radiation that shatters complex organic molecules as quickly as they form. Yet, in the absolute darkness beneath this hellscape, there is a flicker. Life in its most tenacious form persists, miles below the irradiated surface, where the planet's internal heat still bleeds through the crust. Vast networks of aquifers and porous rock exist. Here, in the perpetual dark and under immense pressure, colonies of microbes cling to existence. They are not like life on Earth. They are hyper-specialized extremophiles, feeding not on sunlight, but on chemical energy, sulfur, iron, hydrogen released from the rocks themselves through geothermal activity. Their metabolism is slow, their reproduction a patient, centuries-long process. They form brittle, crystalline mats or exist suspended in briny, subsurface lakes cut off from the universe above for billions of years. This is a biosphere of profound simplicity and isolation. It is a silent, blind, and touch-based world. These microbes are the ultimate survivors, but they are also permanent prisoners. The energy needed for movement, for rapid growth, for complexity, simply does not exist in their sunless, energy-poor prison. Evolution here is on a near standstill, an endless refinement of survival in a single, harsh niche. There is no pressure to develop senses, mobility, or cooperation. There is only the imperative to endure. The surface, with all its lethal energy and potential, remains utterly out of reach. Imagine a spore, a dormant cell, somehow carried upward by a rare geological vent. It breaches into the thin, glowing atmosphere. For a moment, it is flooded with energy, but it is a death sentence. The same radiation that could power a new form of photosynthesis instead shreds its delicate cellular machinery in an instant. The planet's star, the very source of the warmth that keeps the subsurface water liquid, is also the warden of this subterranean jail. It ensures that any attempt to leave the deep sanctuary results in immediate execution. So life remains trapped. It survives, but it cannot thrive. It adapts, but it cannot diversify. It represents a potential that will never be realized, a story that begins and ends in the same dark paragraph. This world is a galaxy in miniature, a portrait of what the Aurora Effect suggests may be the most common biological state in the cosmos. A living planet, yes, but a silent one, where the only witness to the beautiful, deadly aurora is a layer of rock, and beneath it, a slumbering microbe that will never know the light. That shimmering, deadly aurora is a cosmic boundary marker. It separates the universe of the living from the universe of the awake. The core argument of the Aurora Effect is both simple and profound. The very phenomenon we find so beautiful on Earth may be, across the galaxy, a common symptom of a planetary death sentence. It suggests that for life to grow beyond simple microbes, to become complex, intelligent, and curious, it needs more than just water and the right temperature. It needs a fortress. It needs a stable, gentle star that does not erupt in sterilizing flares every few centuries. It needs a planetary magnetic field, a global force field generated by a churning, molten core to deflect those deadly stellar winds. And it needs a thick, robust atmosphere to act as a secondary radiation shield and maintain the pressure for liquid water. Each of these is a non-negotiable condition. Remove one, and the path to complexity is almost certainly blocked. The terrifying implication is that this perfect trifecta of protection might be extraordinarily rare in a cosmos dominated by tempestuous red dwarf stars and silent, airless rocks. Our existence here is not a standard model. It is a statistical marvel. Every breath you take, every sunset you watch, every thought you have is happening under the shelter of a planetary shield that survived billions of years of cosmic bombardment. We are the beneficiaries of a celestial peace treaty that may be one of the universe's best-kept secrets. So tonight, or the next clear night you have, step outside. Look up at the stars, but see them with new eyes. See them not just as points of light, but as suns, most of them volatile and dangerous, around which countless worlds may be trapped in silent, microbial prisons or stripped bare as barren rocks. And then look at our own world, at the stable ground beneath your feet and the protective sky above. See it for the miracle it is, a rare, fortified sanctuary in a vast and mostly inhospitable universe. This understanding does not have to be a lonely one. It can be a catalyst for profound gratitude and curiosity. Stay tuned to the new discoveries from telescopes like James Webb. The data is coming in now, and it will tell us if our galaxy is truly a quiet cathedral or a garden of hidden fortresses, and we want to hear what you think. After all this, do you believe the Aurora Effect means we are truly alone? Or do you hold out hope that life and intelligence always finds another way? Share your perspective in the comments below. The conversation about our place in the cosmos is just beginning.